Hey everyone, my name is Karthik. I'm a machine learning engineer at Arthur AI.
Hello everyone, I am Sahil. I'm a PhD student at University of Washington, and today we'll be talking about FastCFE, which is a distributed reinforcement learning based counterfactual explanation tool. And this work was done while I was interning at Arthur AI. So in this talk, we'll be going over the background, the problem statement, followed by the implementation, system design, and a quick glance at the results. And let's dive right in. All right. So consider a case where you go to a bank to ask for a loan to purchase a new house or a car, and you go to a banker and they take in all your features like your income, your age, your education level, and stuff like that, and feed it into the computer that's in front of you, which is running a back-end machine learning model. And after consuming all your features, it spits out that you are rejected for the loan. As someone who needs money at that point, you would be interested in asking the question, why was my loan rejected? Or specifically, what can I do in order to get the loan? And this is the specific question that counterfactual explanations answer. So for example, it could tell you that had your income been $40,000 rather than $30,000, you would have gotten the loan. Or if you had been a master's instead of a bachelor's, you would have gotten the loan. So there are some desirable properties which ideally counterfactual explanations should follow, and the first and foremost that a modified data point, which is denoted by x prime over here, should lead you across the decision boundary, which is in this case getting you the loan approved. Apart from that, in order for the changes to be realistic, we should be close to the training data manifold that was used to train the machine learning model which the bank is using. There are certain features that have constraints on themselves, and therefore we should not modify them. For example, your race, or you're suggesting that you need to decrease your age. And another constraint to be realistic is that we should follow some real world causal constraints, like if a model is suggesting you to increase your education level, it also needs to take into the account that your age will increase. So these are the properties of a counterfactual explanation that are desirable. There are also certain properties that are desirable from the approach that is generating the counterfactual explanation, and we have enumerated them here. So model agnosticity is the first one of them, which is basically if an approach can work, is model agnostic, then it can work for multiple machine learning models. Black box access is useful if an approach is going to be deployed in a privacy restricted setting in which the machine learning model cannot be exposed to the vendor, and if the approach can only generate counterfactual explanation by accessing the predict function, that's great. And the third one is about being fast. So when these systems are deployed at industrial scale, they need to consume a lot of points and generate counterfactual explanations for them, and therefore we want them to be amortized and fast. So we went over the properties of counterfactual explanations and the approaches that are generating them. And now let's look at how are the approaches that are present in the explainability literature perform on these qualitative attributes. So here in the leftmost column, I have enlisted some of the popular and like the most cited approaches in this research area. As you can see, FastCFE was the first and the only one that could satisfy all of these qualitative properties. And now let's talk about how did FastCFE achieve this. So the main insight here was to train a reinforcement learning agent that could generate a counterfactual explanation for a data point from a given data distribution. And this insight can satisfy all the desirable properties that were mentioned in the slides before, because to train this reinforcement learning agent, you only need access to the predict function of a model, and hence it's model agnostic and black box. And once this reinforcement learning agent has learned a policy to produce a counterfactual explanation for a data point belonging to a data distribution, you can deploy it to produce counterfactual explanation for many data points, and hence it's amortized. And since we are also designing the transition function for this reinforcement learning agent, it can be modified to account for feature-wise constraints and the causal constraints, which are other properties that we talked about. So what is reinforcement learning agent, because we are going to use it here. So it's one of the main branches in machine learning where there's this agent, which is in this case a mouse, which is going to take some actions in the environment it's present, and when it takes some action, it modifies its state. The environment responds to this action by giving a positive or a negative reward. And the goal of a reinforcement learning agent is to learn a policy that can maximize the sum of positive rewards over the length of an episode. So how would this look for counterfactual explanations? So consider a case you have a binary classifier similar to the example that we were previously talking about, the loan example. And your features right now are in the blue side because they are not being approved for the loan. And the goal is for them to cross the decision boundary and get approved for the loan. And how would the setup for reinforcement learning in this case would be, an action would be to modify a feature, either increasing or decreasing. The environment is the machine learning model that is giving you a reward if you indeed cross the decision boundary. Otherwise, if you are still on the negative side, you'll not get any reward. And an agent in this case is the reinforcement learning agent that's trying a bunch of actions by modifying features and trying to cross the decision boundary. And now my friend Karthik is going to talk about the implementation, the system design, and about the results.
Thank you, Sahil. So yeah, now we're going to talk a little bit about the implementation and details of FastCFE and what frameworks we use to build an algorithm to scale it into our platform, as well as build out the algorithm. So the two frameworks we focused on were OpenAI Gym and Ray plus RLLib. Each of these frameworks have a different purpose in designing FastCFE. We utilize OpenAI Gym to define our environment and how much reward an agent will get when it's at any given state taking some type of action. We use Ray and RLLib to do the distributed training and distributed prediction after we've defined this custom OpenAI Gym environment. In order to build a custom OpenAI Gym environment, we need the following four things. The first is the observation space, which can also be considered the full possible set of states. This can be defined using a variety of different types of data types, and we're going to see an example of it in a couple of slides. The next thing we need to define is the action space. The action space is also the full set of possible actions an agent can take. This is similarly defined by the same types of data types that you can use to define the observation space. Next, we have to define a reset function, which is a policy for starting once an episode is completed. And finally, we need to define a step function, which is how much reward will the environment produce if an agent takes an action A at state S. It will also produce the next state that the agent will go to once it has completed that action. So for FastCFE, this is actually one of our most descriptive functions, and we're going to take a look at it in a couple of slides. So in this next section, I'm going to be providing a couple of code snippets about how we define the different parts of the OpenAI Gym environment in the context of FastCFE. So for simplicity, I'll also be using a toy credit dataset, which has three generic features: income, credit score, and education. So to define our observation space, we are going to, first of all, normalize all our features to be between -1 and 1. And we found that this is very useful for training and kind of containing the ranges of these variables. And we define it using this data type called a box, which allows us to define continuous state spaces. And we define it to be between -1 and 1 for our 3 feature dimensions. Next, we can define our action space. And for our action space, we kind of utilize 2 different data types. We utilize the tuple to combine 2 discrete actions. So in our case, the first part of our action will define which feature index we want to move along. So for example, if we select 1 or 2, and that's the index for a credit score or income or education. The second part is simply binary. Do we want to increase along that axis or decrease along that axis? Cool. So moving on, we need to also define our reset function, which is kind of the policy for how do we define an initial point during training and prediction. So to do this, we have it done in separate ways for predict and train. For train, we'll simply sample our initial training data set for the negatively classified data points. While for prediction, we can simply input that starting point and then initialize the custom environment with that data point as the starting point. Finally, we move on to the step function, which is, again, the most descriptive function for FastCFE. So we want to define a function that when given an action and a current state, it will be able to produce the reward that the environment will be able to produce the reward and the next state the agent will be in. So let's walk through this code a little slowly. On the left side here, we are first going to get from the action the feature index that we talked about before. And the second part is going to be, are we going to increase along that axis or decrease along that axis? Next, we quickly define some constants for the reward and if we've completed the episode. On the right side, we see that we want to define what our new state will be. So we will simply index into that feature index that we got before, and we will increment it or decrement it based on what the second part was. Would also like to note that we have put negative 0.05 or 0.05 here. This can arbitrarily be defined as anything. We just chose it because we have normalized all our features to be between -1 and 1. Next, we're going to get our classifier reward, which is kind of an approximation for how close we are to our decision boundary. We'll next get the manifold distance loss, which represents how this data point looks compared to the training data set. And we'll combine these two, return that as the reward to the client, as well as the next state that the agent will be in. Nice. So now that we've defined what the environment, custom OpenAI Gym environment is, we want to define a model that is able to generate counterfactual explanations. So what this would look like, again, for our toy credit dataset example, may be increasing income by $10,000 and increase in education by 1 year. In order to do so, we want to produce an approximately optimal policy which would return the best action at state that maximizes our future expected reward. And our model will, in order to do so, we kind of utilize deep reinforcement learning. And deep reinforcement learning has some benefits where, first of all, it's faster training times because instead of trying to learn this policy, the exact optimal policy, we kind of approximate it using a neural network. Second, we have easy distribution. We are able to distribute these training jobs and prediction jobs across many different nodes in our cluster. And lastly, we want to have near real inference time. So once we finish our training, the prediction part is very, very fast. So we obviously used Ray and RLLib as our tools and frameworks to build out FastCFE. And in general, Ray and RLLib provide a very easy API in Python to distribute machine learning tasks and these reinforcement learning tasks in a Kubernetes cluster and on a single node. So RLLib has a variety of different optimization algorithms right out of the box and provides configurations that you can use for the specific optimizer as well as the generic RL-based tasks. And for our use case, we decided to use the proximal policy optimization, which is a new gradient-based technique. We used it because it has a nice trade-off of ease of use, scalability, and wall time efficiency. Yeah, and now we want to talk a little bit about our RLLib wrapper. Can we wrap some of the code around the native libraries that RLLib provides? And we're going to start with the train side here. Again, sorry for the small font. But the first thing we need to do is define and register our custom OpenAI Gym environment inside RLLib. And this allows RLLib to find the environment and be able to create an agent that can interact in this environment. The next part is we're going to kind of set these hyperparameters. And these hyperparameters are useful because it decides how many episodes the model should use before batching them together to train the neural network. We define what our optimizer will be. We used PPO for this case. And again, we can use any kind of optimizer from the RLLib standard. And now we can go through our training loop. And through every training loop, we'll train the model. And we want to see that our mean reward is increasing, and the maximum amount is 100, which is defined by our custom environment. And we also want to see the number of steps it takes to actually achieve that is decreasing over the training loop as well. So now moving on to the predict wrapper side. Basically, we want to be able to get a counterfactual explanation given any initial starting point. So in order to do so, we can reset the custom environment using that initial starting point. And for every single step it takes, we can compute the best action through the saved and trained model. Note, we have a maximum number of steps. So after 50 steps, we decide that we cannot find a counterfactual explanation and terminate the loop. Cool. So now we can show a brief demo about how some of these concepts look in an actual Jupyter notebook and how we can kind of utilize this out of the box. Perfect. Okay. Yeah, so let's do our basic imports. So I think generically what we're trying to show here in this demo is how we can use FastCFE for a simple German credit data set. So here we're going to do our basics. We're going to load in our CSV file. We're going to break up train test split. And we have also previously created a binary classifier, which is a random forest model. So this is all here. So now with just these artifacts and a little bit of extra metadata, which we talked about with the feature constraints as well as feature relationships, we can specify what these are while inputting into FastCFE. So for example, for our German credit data set, some of the immutable features are, personal status, number of people being liable, et cetera. Features that cannot decrease are something like age, and we have a bunch of categorical features as well. And this allows us to be more prescriptive instead of just kind of treating everything as continuous. We have to input our predict function as well, and we can now create an optimizer. And this optimizer, what it will do is basically create that RLLib wrapper that we talked about in the presentation. And with that, we can train. I don't want to run it live. It takes a few minutes to boot up Ray. If you've used Ray before, you definitely know that. And yeah, so we just want to kind of look through kind of these epochs and how training is going. And we can see that we want this mean reward to increase over time, and we can kind of see that pattern, of course, with some randomness. And similarly, we want to see with the number of steps to be decreasing over time. And we, again, start to see that, again, with some randomness. We have some code to use hyperparameter tuning using RayTune as well. We're going to skip this part, it's not really relevant. Yeah, we can evaluate how well our model did with some baseline metrics. We talk about validity, and we're going to talk about that more in a few slides. Yeah, so here I want to showcase like how a counterfactual explanation will actually look for a data scientist or a machine learning engineer who's trying to evaluate some type of machine learning model. So what we'll see is that what are the variables that actually that need to be changed in order to flip your decision. And we want to see what the new value is versus the old value. And we can see this for a variety of different counterfactual, or a variety of different inference points. I would also like to note that these are categorical variables, so this numeric difference doesn't really mean much, it's just that this is a different kind of category. Awesome, and now we can go back to the slides and talk a little bit more about our system design and how we used Ray and RLLib to actually incorporate it into our Arthur platform. Awesome. Yeah. So we had three major goals when trying to figure out what tool to use to deploy this algorithm. And the first one was to be able to deploy a service that computes these counterfactual explanations in real time. In the Arthur platform, users send us their inference data, and we want to be able to stand up a service in our backend that when sent in a new inference data point, it can return that counterfactual explanation very fast. Second, we want to be able to deploy a service that is able to train FastCFE, and this training should include training on a single node with multiple CPUs, as well as on a Kubernetes cluster, as we are a Kubernetes native application. And then thirdly, we want to reduce the runtime for using Ray and RLLib through distribution over kind of a simple stables baseline implementation. So we break up our design into two phases, training and inference. And in this slide, we're really going to discuss our training architecture. And in the first step, our user sends us their reference data and model artifact, just kind of how we showcased on our demo. And both those things will be sent into the Arthur platform, and they'll be bundled together to kick off a Kubernetes native scheduler for our FastCFE training job. With this training job, we are able to utilize Ray and actually do the training on a cluster, a Kubernetes cluster, using multiple nodes. And we also like to note that this is a one-time training job, so we're able to utilize as many nodes as possible to really speed up that training. So once training is done, we save that model artifact to S3, and deploy our FastCFE service using that model artifact. Now this makes inference very easy because we already have our deployed FastCFE service. Our clients send us all their inference data that gets ingested again into the Arthur platform. And now since we've already stood up our FastCFE service, any data scientist or ML engineer who is using Arthur can simply click on compute counterfactual explanation and get back that explanation in real time. Awesome. So now we can talk a little bit about the results. And the two major results, kind of metrics we wanted to look at were performance metrics, and namely how did FastCFE compare against other state-of-the-art counterfactual explainers. And the second is we want to look at the training time. What benefit did we gain from using Ray and RLLib and how it helped us distribute across our cluster? For this, we kind of looked at five data sets. 3 were open source and 2 were company sensitive. The 3 that were open source were German credit, adult credit, and credit default. And the other 2 were kind of encoded with several different types of variables. I'd like to also say that these data sets represented a wide range of number of data points as well as number of features. So the first thing we look at is our performance metrics, and we look at validity and mean inference time. Validity is the total number of counterfactual explanations actually found divided by the total number of negatively labeled class data points. So this number is actually represented as a percentage. The second thing is we wanted to look at that mean inference time, which is the average time it takes to compute a single counterfactual explanation. So looking across our 3 open source data sets, we see that FastCFE gets a validity of at least 97.3% and actually achieves a perfect score in the German credit data set and 99.9% in the credit default. We also see that our mean inference time is an order of magnitude faster across all the different methods. Next part is we wanted to look at the kind of training time and how the training time of using Ray and RLLib compared against a simple stables baseline implementation. We see again across the stables baseline implementation in some case took very long and did not even finish on data sets. And we noticed that when using Ray and RLLib on a single node 8-core machine, we were able to achieve 6x time in train time savings. So in conclusion, we hope this presentation provided you a good overview of the following concepts. 1, counterfactual explanations, what they are and how are they useful in industrial and explainability applications. 2, reinforcement learning. How do we implement a production level reinforcement learning model into an existing system? And the third is the power of distribution, how we can achieve tremendous savings by using scalable and distributed reinforcement learning frameworks such as RLLib. For more details, we have a couple of blog posts. You can QR code if you want. The first one talks about more of the algorithmic side of counterfactual explanations and FastCFE, while the second one is more of a practitioner guide of how to define a custom OpenAI gym environment and define some basic RLLib wrappers. I can leave this up also, but thank you. These are emails. Any questions?
Hi, thank you. Can you talk a little bit more about how your classifier relates to the reward signal? You mentioned that was tree-based. How do you derive the reward from the distance in that case? And also, your RLLib agent's performance will be dependent on the accuracy of that classifier. Have you separated those benchmarks and sort of done an analysis of those independently? Thank you.
Sure, yeah. So I'll get the first part, you get the second part.
Okay, I can answer the first part about the reward system. So you can train, like for example, if you're using a neural network, you could simply, if the data point is indeed crossing the decision boundary, then you can give a reward of say +1 or whatever. And if it's not crossing the decision boundary, then you can penalize a small amount for taking a step, but not give any other reward. And that's a generic reward thing you can use with any model. So that makes it model agnostic. You can use trees or any model for that case. And
Rewards.
I can.
You don't have a varying magnitude of rewards. You just have a +1, -1 type of reward.
+1 and like -0.05, something like that. For like,
I see.
If you just penalize for a step, so that we also wanted to encourage to cross the decision boundary as soon as possible. So you want to minimize that steps. So there's a small penalty for taking a step and not crossing the decision boundary. And if you indeed cross the decision boundary, there's a large positive reward. So yeah, that's not a huge disparity over there. Yeah.
Okay. Thank you. One more question I'll tack on here. The immutable features, how does that work with the agents in terms of reward if an immutable feature is selected by the agents? How do you account for that?
It's the exact same thing. Like if the agent chooses immutable features, there will be no change in the state, and there will be a small negative reward.
Okay.
And you had another question about RLLib, which I think Karthik can answer.
How does the performance of the classifier relate to your benchmarks?
Yeah, that's.
I don't think I have an answer for that on the top of my mind. I think the better the model is, the more performant would be the reinforcement learning agent. But even if the accuracy of this model is like low, the reinforcement learning agent can still learn how to cross the decision boundary. So the accuracy of the machine learning, the binary classifier would not affect the efficacy of the reinforcement learning agent much.
Sorry, just for the question before the question is, do you train a different policy per classifier?
Yeah.
Okay, so do you, have you played at all with warm starting policies, like doing some sort of transfer learning so you can cut down your training time?
We haven't actually tried that. That's a good suggestion.
Good to know, yeah. I didn't know that, no.
Cool. Sorry, one other question. I was wondering also about algorithm choice. So PPO generates a stochastic policy. I was wondering if you have a sense of how undecided the policy is at any given stage. For instance, what's the relative weight on the logits in one step? Like, would it rather, is it like very preferentially going one direction, or is it kind of undecided?
Yeah, so when I was running a lot of experiments with this earlier on, is we noticed that like it directly does relate to the logits that are being outputted from the classifier, right? So I think that was one of the things that we talked about is in practice, like using the logits from the classifier allow the agent to slightly understand where it's moving relatively to this decision boundary, because you get the positive and negative class predicted probabilities. So we were testing a lot with that. I think warm starting would be a great suggestion for like speeding up, especially if you're using like a same class type of problem like credit risk or something. Thank you.
There's, I think, one more question there.
Hi, thanks for a great talk. So I'm not super familiar with counterfactuals, so please correct me if I'm misrepresenting something. But at least at a high level, the goal of changing the input as little as possible to change the classifier's output feels very similar to me to adversarial training. So I was wondering what you see as the benefits of training this reinforcement learning model to do something similar, which feels like a more complex approach to me, at least on the face of things.
Yeah, I can answer that question. So that's a very good point that it has very lot of similarities with adversarial learning, and that comes often in the literature and on Twitter all the time. The main difference lies in how the features are being altered. So in adversarial learning, you would not consider which feature is immutable or something. In this case, you would want to give that advice to a person, so you have to place some real world constraints. So that's one thing. But to answer the more in-depth question which you asked, like why did you choose reinforcement learning and not something, let's say, just like FGSM, like or gradient descent? The answer for that question is that using there have been many approaches, like if you remember the table that I presented, those most previous approaches use such a thing like a gradient descent based approach. It's just that it's not amortized, so you have to run the gradient descent for every new data point, whereas in this case you do not need to. So that's the motivation behind using RL. Does it answer your question? Awesome.
This is more speculative. Can you, do you guys have an uncertainty estimate or a distribution of outcomes that, or thought of a way of doing that? So, for example, in your credit score assignment, you say it could be, instead of $30,000, it was $40,000 was the income, but there's also, I guess, a distribution of that plus other features. Have you thought about a way to do that?
Yeah, they could be like, obviously there are multiple counterfactual explanations that could exist for a data point. So you could weigh them according to different norms or something. We just choose the one that had the minimum L2 norm, I believe, from the data point. But they could be, you could produce multiple counterfactual explanation and present all of them and give the user the freedom to choose whatever they prefer. Yeah.
Okay. Thank you, everyone.
Thank you so much.